The purpose of this video is to discuss the three phases of water. Water comes in as an ice form, a liquid form, or a steam form. You're quite familiar with these, and I'm sure you've experienced them in your everyday life. When water is ice, it is what we call a solid. When it's liquid, of course it's liquid, and when it's steam, it's a gas. Now, energy is required to go from solid ice to gas or steam. When we're adding energy, the temperature of the substance does not just increase directly like you would expect. Instead, it makes a sort of heating curve. So we're going to discuss what that heating curve is, first conceptually, and then we're going to discuss what it means mathematically, or when we're plugging them into various equations. So first, let's do conceptually. When we are talking about the heating curve, we're going to draw our axes like so. Down on the x-axis, we are going to label it energy added. So this is usually added in the form of heat. So you can heat it on a stove, or maybe just the sun. It's in the sunlight, and water is naturally heated that way. On the y-axis, we're going to write temperature, and usually we do that in degrees Celsius. So let's start off with a very low temperature. We could say maybe something like -10 degrees. At -10, ice will begin to, as you add energy, ice's temperature will begin to increase like so. At a certain point, what happens to ice? Well, at 0 degrees, it melts. At that melting point, however, the temperature doesn't change. Instead, the ice just changes from a solid to a liquid. After that point, if energy is continually added to the water, it's going to increase in temperature again. This time it's going to increase for quite a while until it gets to the boiling point, which is 100 degrees Celsius for water. At this point, all the energy that's going to be added to the system will go to breaking the bonds between the water to go from liquid to gas. And at this point, after it's completely all converted to gas, it will then again increase in temperature. So notice that we see flat regions. These flat regions occur right here and right here, and they accompany what we call phase changes. The slanted regions, right here and right here and right here, the physical state does not change. It's solid right there, it's liquid right there, and it's gas right there. So all the energy is going to kinetic energy, or increasing the temperature of the substance. Whereas in the flat regions, all the energy is going to potential energy, or changing the substance from a solid to a liquid, or from a liquid to a gas. Now let's put some numbers to these regions. So we've already dealt with one of these numbers in a previous slide. You might recognize this number as 4.18. Remember, this is the energy, or the joules required to change 1 gram of water 1 degree Celsius. So whenever we're dealing with liquid water along that region of the graph, we are going to be using that specific heat. So we're going to call this the specific heat of liquid. Down in this region, down here, we are going to be using a different specific heat. This will be the specific heat of ice, or solid water, and its value is 2.1 joules per gram times degrees Celsius. Now you've probably guessed that gas also has a specific heat, and its value is its value is 1.9 joules per gram times degrees Celsius. So all of these you'll notice have units that have Celsius in them because they involve a temperature change. Now the solid or the flat regions do not involve temperature changes, and we represent the value of energy required to change them by delta H's or enthalpy of, in this case, it's fusion, FUS, and in this case, it's the heat of vaporization, VAP. The heat of fusion is 333 joules per gram of water. So that's the energy required to take 1 gram of water and cause it to melt. The heat of vaporization is 2,257 joules per gram. So that's the energy required to take 1 gram of water and turn it into 1 gram of steam, so from liquid to gas. You'll notice that the heat of vaporization is much larger than the heat of fusion, and that's not too surprising because when you think about an ice cube melting, it goes from a solid to a liquid state, but all the water molecules still pretty much stay together. They're just now no longer stiffly in a solid crystal structure. They're instead more fluid and can move around more. With the heat of vaporization, however, the molecules, most of them have to completely break their bonds with each other so that each water molecule is now no longer touching and they turn into gas molecules. So this is going to require a lot more energy than, say, just melting a substance. So what does this mean in terms of math? Well, we're going to now use this graph to do some equations. But before we do that, I'm going to write the numbers nice and neatly for us so that we can see them more clearly. All right, so let's do our first one. Let's call this one the specific heat the specific heat of ice. You'll also see it written as C with a subscript S, and in this case that value is 2.1 joules per gram times degrees Celsius. So that's the specific heat of ice. So that's when we're just dealing with solid. So this is for when we're just dealing with solid ice. Now the next thing we're going to do is the next region of the graph, you'll remember, is the heat of fusion. And the heat of fusion is represented by a delta sign. I don't have that on my keyboard, and an H. And in this case, the delta H is equal to 333 joules per gram. Now you might notice that some of these values might change when you look at different books. That's because they are dealing with different pressures, but we're just going to use some of the commonly accepted values. The next region of the graph is the specific heat of liquid water, and that value is C with a subscript L, and it's 4.18 joules per gram times degrees Celsius. So once again, this is going to be dealing with just liquid form. And here again, it's from when you're going from a solid to a liquid. Our next value was the heat of vaporization. and that value was also represented by a delta H, and its value was much larger because it requires a lot more energy to go from liquid to gas than it does to go from solid to liquid. So that was 2,257 joules per gram. So once again, this is when you're going from a liquid to a gas. And finally, we are going to do the specific heat of gas or steam. And this value was C, represented with a subscript G, and its value is 1.9 joules per gram times degrees Celsius. And once again, this is when we're dealing with only the gas phase. Okay, so now that we've got our values down, we are going to use them to do some calculations. So let's do a problem. Okay, in this problem, let's see what is the energy required to melt 100 grams of ice. So you'll notice here that there is not any sort of temperature in there, so we're most likely dealing with a heat of fusion. We also see this word here, melt, which tells us it's going to be a phase change. So melting indicates that it's going to be going from a solid to a liquid. So let's find that region or that value that we use to just go from a solid to a liquid, and hopefully you've identified that in your notes as the heat of fusion, delta H FUS, which is equal to 333 joules per gram. So we want the energy. Notice the question that we want the energy, and that's going to be represented by a value Q. So all we have to do is, in order to get the energy, we just need the joules. So if you'll notice that in this constant, it's 333 joules per gram. So we need to get rid of those grams. So how do we do that? Well, we just multiply it by the mass, or the grams that are in the equation, or in the problem right there. So our equation is going to be Q equals 333 joules per gram. Remember, we want to get that joules all by itself, so we need to get rid of the grams. So we'll multiply it by 100.0 grams. So when we do that, our grams nicely cancel out because one's on the top and one's on the bottom, and we'll be left with 333 times 100, or 33,300 joules. Now that's a pretty large number, so what we probably are going to do is want to put it in kilojoules. So we can do that by just dividing by 1,000, or 10 to the third, because remember, kilo means 10 to the third, or 1,000. So we'll get 33.3 kilojoules, and that's our final answer. All right, so what if we want to involve something that's changing state and changing temperature? So let's have a look at one of those problems next. So when we are trying to change state and temperature, we are going to have to use two different values from our graph. So let's see how much energy is required to change 10 grams of water from ice at -10 degrees Celsius to liquid water at 50 degrees Celsius. Make a little more space there. So don't forget to put your degree signs in there as well. Okay, so let's think about what part of the graph we're dealing with. So we're starting, I'm going to draw a little sketch of the graph down here. So we're starting with ice at 10 degrees, negative 10 degrees, and we are going to turn into water at 50 degrees. So this is all in degrees Celsius. So remember, if we start as ice, we have to first increase our temperature until we get to 0. At 0, the ice begins to melt. And then after that, as we continue to add energy, the temperature will increase until we get to 50 degrees. So you'll notice there's 3 different regions we're dealing with. 1, 2, 3. So take a moment and look up the values that correspond to each of those regions. So what we're looking for first is the specific heat of ice or solid water. Then we're going to be looking for melting, which is the heat of fusion. And finally, we're going to be looking for the specific heat of liquid water. So if you need to pause the video and look them up, that's great. Make sure you know where they are in your notes. And then you can check your answers with mine. So the specific heat of ice is 2.1 joules per gram times degrees Celsius. The heat of fusion is 333 joules per gram. And the specific heat of water is 4.18 joules per gram times degrees Celsius. So now we're going to use these to perform our calculations. So let's start with our first region. Let's start with our from negative 10 degrees to 0 degrees Celsius. So in that region, we're going to be using our specific heat. So remember, the equation for using specific heat is Q equals C times M times delta T. So that means this is going to be equal to 2.1 joules per gram times degrees Celsius times the mass, that's up here in the problem, 10 grams, times the change in temperature. So we're only going in this problem from negative 10 to 0 at first. That's the only part of the graph, the region right here. That's the only temperature change for that region. So we're going to use 10 degrees Celsius. So you'll use your calculator to calculate that, or you can do it in your head. And you should get 210. What are our units? We cross out our degrees Celsius and our grams, and you just get left with joules. So that's our first part. Now we're going to go to our second region. Our second region is just this part right here where the melting is occurring. So it's going from a solid to a liquid. So remember, when we're doing that, we're going to be using our heat of fusion. So we're going to be using this value right here, our heat of fusion. So we're going to once again have Q, because we want energy, equals. Our heat of fusion is 333 joules per gram. So it's very similar to our specific heat equation, except because there are no degrees Celsius down here, we don't have to multiply it by a temperature, we just have to multiply it by the mass. And the mass stays the same. So our grams cancel out, and we're left with 3,330 joules. All right, so far we have two values. We have the energy required to heat the ice from -10 degrees to 0 degrees. We have the energy required to melt the ice. And now, finally, what's our last part? Well, let's have a look again up here. Right here, this section is where we're going next. So we're going from 0 to 50 degrees Celsius. So let's have a look at that. We're going to use our specific heat of water in this equation. So it's 4.18 joules per gram times degrees Celsius times 10 grams times, this time our temperature change is 50 degrees Celsius because it goes from 0 to 50. So you'll notice that it has the same three parts: specific heat, mass, and temperature. Just like up here where we also had a temperature change, we had specific heat, mass, and temperature. The difference being here we use the specific heat of solid water, and here we use the specific heat of liquid water. So let's calculate that. 4.18 times 10 times 50, and you should get 2,090 joules. So now we have three values. We have the specific, or the energy required to change the ice from -10 to 0 degrees Celsius, the amount of energy required to melt the ice, and the amount of energy to increase the temperature of the water from 0 to 50. So the question of the problem, however, asked us how much energy is required to change the water from ice at -10 to liquid water at 50. So we're going to have to change that. We're going to have to add all of those values together. So 210 plus 3,330 plus 2,090. So let's see what the answer is. $210 joules plus 3,330 joules plus 2,090 joules. So the total is 5,630 joules. That is our final answer. Now, a challenge for you is to figure out how many significant figures our answer should be in. So I want you to have a look at that, and if you can tell me the answer to that, I will give you a free homework, and explain your reasoning, I will give you a free homework pass. In the meantime, I'd like you to turn to your notes, and you are going to do on page 9, you are going to do problem numbers 1 through 3 in your notes.